All right, so it says, suppose a certain set of data is satisfied by the standard logistic function. What is the carrying capacity and on what intervals is its first derivative increasing? Okay, the logistic always looks something like the following, something like that. Actually, let me spread it out a little bit more. Where it rises and does something like that. Okay, so it's actually always increasing, which is kind of interesting. We can show that. Are you seeing my screen?
Yes, I am.
Okay, just making sure. It's always increasing. Every logistic model is always increasing. So it's increasing from 0 to infinity, something like that. Now, we could show it with calculus. With calculus, we have to take a derivative. We have to figure out if there's any critical points. If there are no critical points, you just test a value, and you'll see that the derivative is positive. And I can do all that if you would like. The carrying capacity is the limit as x goes to infinity. Basically, what happens? What value does it approach? And so, like the there's various logistic models, but it's always a over b plus there's this e thing over here. It's always this part right here, whatever a over b is. So in this case, it's 1 over 1. Again, we could maybe show that by doing some things, but this is kind of a graphing problem, kind of. But it's multiple choice. So would your instructor be okay with that? And I assume they would be.
With doing multiple choice?
Yes, like
Yeah, most likely.
yeah. So the answer here is yours is 1 over 1, which is 1, and it's increasing from 0 to infinity.
Okay. There's also an answer just when you scroll down to the bottom of the PDF.
Okay. Yeah, just let me know if there's anything inconsistent with that that we just talked about. So, oh, you know what? Sorry, this is not asking. Okay, first derivative increasing. So the functions, the f of x is always increasing from 0 to infinity. F prime of x, well, we have to take the derivative of its derivative. It's basically asking where is this thing concave up or concave down. So we actually do have to take a derivative of this. It seems a little out of scope for what we're trying to do here. So I'd like to move on to another problem that actually might benefit you on a quiz or a test, if that's okay.
Let's do it.
Okay. Boy, these are awkward. Number two is a function, and they give you the graph, which between, okay, so that we had dialogue about this. So they give you the graph, and the graph shows that there's some area from -2 to 2. I'm sorry, -1 to 1. What the instructor is trying to show you here is that there's kind of this negative area,
Sure.
and then there's this positive area. Okay. And so when they ask for total area, they're asking for the absolute value of the function.
All right.
So this was a calculator problem. This was a like, okay, go to your calculator, do that. Now we could do it by hand, but it would appear this is very calculator heavy. Okay, so if we do the integral from -1 to 1 f of x dx, okay, this gives us the net area. Okay, but if we do the integral -1 to 1 absolute value f of x dx, this gives us the total area. And and for this problem, you want the second one here.
Yeah.
So that's where you do that math 9 thing, fn int, and you end up getting.
What do I put in for f of x?
So that's up here, this function right here.
Oh, okay. How do I put the absolute value in there?
That's under math ops, I think.
Math ops. Okay.
I believe. Please confirm.
Oh, there it is. Okay, so it's in my calculator on TI-94. I go to math and then go to the second menu and and it should be the first one. Absolute value of x cubed. X cubed plus x squared equals 2x plus 1. And it should be d of x, right?
Yes.
Here's what I get. I get a 3.06.
Give me that number again.
3.06.
So they call it 3. So that's probably it. Let me just make sure that that is correct. Yep, that is correct.
Awesome. If any of these are awkward, it's probably because it's from the teacher's assistant. If you look
Okay.
at the do you want to go through the math 13 extra review one? That's the one that my actual instructor wrote. And then we
Okay.
can go through this one again.
Let me pull that one up. Yeah, I mean, this is your more standard test. We should do this other one. Okay, here we go.
Mhm.
Yeah, let me snip that in. And this is like,
This is probably the guy that I'll like put a lot of my I'll put a lot of on my cheat sheet.
okay, so this is number 1. And it asks for critical points, and you're supposed to say, oh, that's derivative. Okay, it's
Mhm.
derivative equal to 0. So let's take the derivative of this function. It's power rule. Okay, it's 12x cubed. Good.
12x squared and 0.
And you set it, yeah, and you set it equal to 0. And here you need to do a Gcf factoring. So you say, oh, there's a 12x squared in both.
Mhm.
And then you set each term equal to 0. So you set 12x squared.
X equals 1 and x equals 0.
Yeah, so x equals 0 and x equals 1. And these are your critical points. So like and one of the things that I find challenging is like, well, how do you literally need to say some critical points, x equals 0 and 1. Like you have to do that. The next thing is you make what's called a sign chart. Now I use a number line. I noticed, well, I guess your instructor kind of does. And I label the 2 points, the 2 critical points there. And then what you want to do here is you want to test values in each interval. So you want to maybe test like -1 or 1/2 or 2. And you test them in the derivative. It's very critical that you hear that and remember that it's in the derivative. Okay.
All right.
And more specifically in the factored form. The reason is because you care about the sign of the answer, not the actual numerical value of the answer. So for example, let's put in 2. 12 times 2 squared is some number, but it's positive. 2 minus 1 is positive. It's a positive times a positive, and that gives you a positive here. And that's the analysis you know. When I was a student, I say this, and you want to put the number, you want to get a number out, but you've got to transition and say like, okay, I just need to know whether it's positive or negative. Because like 1/2 squared, I don't know what that is, but times 12 is positive. 1/2 minus 1 is negative, so it's a positive times a negative. That's a negative. You only care about the sign of this. When you put -1 in here, you get -1 squared. That's positive times 12 is positive. -1 minus 1 is negative. Positive times negative is negative. Okay, so now how do we figure this out? If it's going from negative to positive, that's a min.
Mhm.
If it's going from plus to minus, that's a max. And then the other possibility is minus to minus, plus to plus, and these are both nothing.
Yeah.
Okay, so what you have up here is you have a min. This is a min at x equals 1 because it's going down and then up.
Okay. And the negative is nothing.
Nothing, yeah. Another point here is that sometimes, I don't know if this has the solutions on it, sometimes they actually want you to like get the y value. It's not good enough to say there's a min at x equals 1. They actually want to know where it occurs. So you get the y value from putting it back into the original. Does that make sense?
Yeah. Put the y into the original. All right.
Yes. Yes. It's only if it asks. Like this question is somewhat unclear because it doesn't say isn't say that specifically.
Mhm.
Okay. if you're okay with that one, we'll move on to question 2.
Good to go.
So for some reason, your instructor here in question 2 is giving you the original and the derivative and the second derivative. I wouldn't expect that. I would expect you're gonna have to take derivative and factor it and take another derivative. Okay, but they've given it to you here. So it doesn't ask for it, but you still need critical points to answer min max. The critical points are when the derivative, which is 6 times x plus 3 times x minus 2, when the derivative equals 0. So when x plus 3 equals 0 or x minus 2 equals 0, x equals minus 3, x equals 2.
Fair enough.
Okay, so we draw a number line. Minus 3 and 2. I'm not like using the grids. These are just spread apart here. And we test points. Okay, we test numbers in each region. 0, 3, and minus 4, for example. It's up to you, but you test them back on the derivative. Again, you'll hear me say the same thing over and over again. It's the sign that we care about. So like 6 is always positive. So when we test a number over here to the right of 2, like 3 plus 3 is positive. 3 minus 2 is positive. Positive times positive times positive is positive.
Okay.
0, again, like I know you want to get the numbers, but you get 3 here, but I just say positive. 0 minus 2 is a negative.
So it's
Positive, yeah, positive times negative. And this one over here, when you put a negative in, you get positive.
Negative, positive.
Yeah, so that becomes positive. They do not always alternate in sign, even though you might see a few examples in a row where it does.
So it looks like a -3, it's a maximum, and then
That's a max, yep. And then that's a min.
Yeah, min.
Okay. Now you feel really good about that, but there is a bit more. It says, where are the inflection points? Inflection points. Inflection points come from the second derivative. Inflection points, f double prime of x, which equals 6 times 2x plus 1, setting that equal to 0. So you set 2x plus 1 equal to 0, x equals minus 1/2. Okay, now that doesn't guarantee that it's an inflection point. You have to do another sign chart again. Okay, so you just put in minus 1/2 here.
Okay.
And you test a point to the right and to the left. Now you could use the same points as above. That really doesn't matter. I'm going to go with 0 and -1. Just be sure you actually choose the point, left and right. I mean, that I've seen some weird stuff happen on tests with students. So again, 6 is always positive. 2 times 0 plus 1, that's positive. Positive times a positive is positive. -1 gives you a negative in here. This is negative. Okay, so it's an inflection point if plus to minus, minus to plus. If it's plus to plus, minus to minus, it is not an inflection point.
This one should be an inflection point.
It is, yes, at x equals minus 1/2.
Oh, all right.
Okay.
Are there any more inflection points?
No, they only occur where the second derivative is equal to 0. That's where they possibly occur. There's only one place where it possibly equals 0 here at minus 1/2. So like you want it to, but it doesn't.
What would it actually look like on a graph? Like, how would you identify it? Would you like put a line through it? Or would you just?
I'd have to graph it, although your instructor made a mistake here. This is probably a 2. It's some sort of cubic. So like the cubic function has it starts low and goes high and like that. So it's right there. It's right there where
where it changes. Oh, okay.
Yeah, concave, in this case, down to concave up.
I see what you mean. All right, on to the next one.
Okay. So these are, my experience is you're gonna definitely get a question like number 3 on your
She said that
test.
she's not gonna do the graph thing. She just wants us to identify all the stuff.
Oh, from the graph.
Yeah.
Oh, okay. Well, then we shouldn't do it. We shouldn't do this. I should make up one, and I should make up a graph and go backwards. Would that be okay?
All good to me.
All right. All right. So here we go. Make your little graph here. I made something up. Here we go. Okay, so here's a graph that Matthew made, and I won't tell you what it is because it doesn't matter. But what you should first do, the first thing you should look for are what are called critical points, and that's where the derivative is equal to 0. Basically, horizontal tangents. So I see one kind of here, and I also see one kind of here. Do you see that?
Yeah, I see it.
Okay. So we could say f prime of x equals 0 when x equals, and you got to just, in this case, I didn't give you nice numbers, but let's say minus 1.75. I think it's actually pi over 2, and then x equals 0. Okay. So the next thing you can do, though, is you can say, well, where is f prime of x increasing?
Just from eyeballing it?
Well, where is the derivative? Where is the function going up and to the right?
From -3 to the 2 point something.
Yeah, so we'll call it -3 to -1.75. Anywhere else?
Where it's increasing?
Yes, going up and to the right.
Oh, then from 0 to infinity, basically.
Yeah, I stopped it at 1, but yeah, you can go on forever. Where is it decreasing?
Decreasing from the -1.75 to 0.
Okay. The next one I could ask you is where is f prime of x greater than 0? Where is it concave up?
Oh, concave up. It's from -1.75 to 1, or
Nope. The inflection point is probably somewhere like there.
Oh, never mind then. So
Okay,
it'd be
so
like,
you only use the critical points for the first derivative. You got to find the other ones for the inflections.
so that looks like a -0.8 to 1.
Yes, and then concave down would be on the other side.
Mhm.
Okay. I mean, that's it. Like, if you're given the graph, it's not that hard to kind of pick out these things. It's much harder to go the other way, where I tell you what's happening, or I tell you like, oh, it's increasing, or it's decreasing, or it's equal 0. That's what's harder to do.
All right.
So I really I know what you said, and I'm not saying I don't believe you. I'm just like, I would just make sure that that's truly what you're going to get, because it's way harder to go from the information to draw the sketch.
All right.
We'll move on to question 4 here. It's also tougher for them to grade, which is why I don't think they do that, because you get too many, oh, I didn't. Anyway. Okay, it says given the function right here, great, we got a function. We need to find the critical points. So critical points come from the derivative. So we need to take a derivative of this function. What is the derivative of this first term?
Oh, this would be 3ax to the second, and minus
minus
12x.
Perfect. You set it equal to 0. Then you need to factor. So you can factor out a 3 for sure from both. You can factor out an x from both. So it becomes ax minus 4.
All right.
So you set this equal to 0. 3x equals 0. Ax minus 4 equal to 0. X is 0. X is 4 divided by a.
All right.
Okay, so that feels good. And it just asks, this one's much more clear. So it says just find the x values. Whereas when we looked at previous, like the earlier problems, it says determine local max and local minimum. That to me suggests you need both x and y, but we didn't do that. But when it says just the x value, which it does down here in 4a, then we just do that.
All right.
Okay. Now, to be fair, we're really supposed to actually draw a number line here. Problem is, though, where do we put this? Because a could be
Anywhere.
It could be positive or negative. If a is positive, it's over to the right. If a is negative, it's over to the left. Maybe you can go to your instructor and get a few bonus points for pointing that out here. That really, it should say like a greater than 0 or a less than 0 on this. Okay, part B. Part B is inflection points. Okay, so you need to find f double prime of x. You have to set it equal to 0. Okay, but you do not use the factored form. Okay, so if you go back f prime of x, you go back to the 3ax squared minus 12x. This is what you want to take the derivative of, not the factors, because the factors have you using product rule. Right, if you go back to this right here, which is the derivative, you don't do product rule here. That's horrible. It's messy.
Ooh, this is 6ax there.
6ax
Nice one.
minus 12. You set it equal to 0.
Mhm.
Solve for x equals 12 over 6a, which is 2 divided by a. So basically like what that says, and it's kind of relevant to this, let's just say 4 over a is here.
All right.
Sorry, let me actually move that for the moment. So let's say a is 1. Okay, that would make that 4. Down here, your critical point's at 2 over a, that would put it at 2. Do you see that?
Yeah.
Like a over 2 would be here. Okay. But let's say, yeah, and so that's really wrong. 2 over a. Oh no, there it is. Okay. So so like there are a few things you can do. Like you can try to like sort of graph this, and some of your WebAssign, well, you're not doing WebAssign, you're doing Wiley. Sometimes they ask you for this kind of stuff in there, but that's it. I mean, that's your final answer for that. They're kind of symbolic. It's kind of like, well, we don't give you the value, so where is it? And you just got to use your properties of derivatives. You got to know that critical points come from taking the derivative and setting it equal to 0. Okay, so number 5. It says find the value of k that will make f of x equals kx squared plus natural log k times x have critical number at x equals 2. So that means we need to take a derivative. We need to find f prime of x. So kx squared derivative is 2kx. That's power rule. Ln, the derivative of ln is 1 over kx times the derivative of kx, which is k. Is any part of that unclear?
I remember that it was like, so ln derivative is just 1 over the.
Yes. Yes. So this becomes 2kx plus 1 over x equals 0, because the critical numbers come from setting it equal to 0. Now, normally you solve for x, but they're giving you x. So you take your x, you plop it in here. So you get 2 times k times 2 plus 1 over 2 equals 0. You get 4k equals minus 1/2. So k equals minus 1/8.
I guess that's the end of that.
There's nothing more to do there. I mean, it doesn't say to like show it or prove it, but like you would, like if you're in a really rigorous math class, they would want you to, determine that, oh, the domain is from 0 to, well, in this case, it's actually the other way. It's actually minus infinity to 0. They'd want you to put that number in for k, and then they'd want you to put in critical points and do a bunch of stuff. But that's where you're done. You're done right there.
All right.
I'm overly complicating it.
Next.
Okay, so 6 is a graphing problem.
Mhm.
So if you have any, I would recommend graphing this one if you've got that calculator handy. I'm going to graph it in Desmos, but I'll keep the window here. Now notice, this is very important here. The step size on the x-axis is 1, the step size on the y is 5. Those are your ticks. You'll see an x tick and a y tick. So in your problem, your x tick is 1, your y tick is 5.
Okay.
So if you got that handy, I would graph it. I'm going to graph it on my side also. And I'm going to just fix the interval here to be -2 to 4. and minus 20 to 20, which I don't really understand why. Is that right? X cubed minus 3x squared. I'm gonna go
Yeah,
back
yeah,
and
yeah.
look.
Yeah,
It
X
just
cubed. Yeah.
okay.
How do I write this in a calculator again? So
You go x caret 3 minus 3x caret 2,
oh, from plots. Okay.
and you want to go to zoom window, or window. I don't. If you would like, I can get the TI virtual calculator out to show you. Just let me know, and I'll.
I'm figuring it out. That's fine. But
Okay.
thank you.
So you get a graph that looks like the following here.
Mhm.
There's that,
Yeah, I got something like that.
and then let's see here, 2, 2. It's kind of right there. We'll say so. It looks something like that.
Yeah, it dips down over two,
And
and
then
then
it
it just
hits
goes straight up.
It's a 3. Look at something like that. Like that's kind of what I would be looking for if I were grading you. But then we need to label as ordered pairs the critical points and the endpoint. So for me, there's a critical point right there at 0, 0, because the horizontal tangent is 0. Like there's a horizontal slope there of 1. There also appears to be this one there at 2, at x equals 2, right here. Okay. Now, if you're really clever with your calculator, you can use that second calc min/max to find it.
It's a second calc min max.
Yeah, this in case you want to min. And when you're doing it on the calculator, you have to choose the left bound, the right bound, and then guess. And you always guess at the right bound.
All right, I'll go for the middle one first. Here's this one.
And if you want to do the max, you get this over here. This ends up being at 2, and then you plug it back in. Like this one's easy enough. I might just tell you to do it by hand and just use the graph. Ends up being -4.
Mhm.
Okay. The endpoints, you're literally checking the endpoints. You're literally checking what's going on at -2, what's going on at 4, and you're just getting the y value there. So you're just substituting that value in. Looks like it's -20. Then similarly, you're doing it over here at 4, and you get like 16. I was going to say 15. There's no calculus in this other than maybe the critical points, but you actually could do this without just a calculator. There's no like formulas or anything needed, no derivatives, just kind of do it. Okay, let me know if I can move on from
This one.
this one. Yeah,
Yeah, that's fine. On to 7. Or
there's
with the stuff down there.
yeah, there's more down there. So this is really interesting. This is actually a good question. We're going to do it piece by piece here, because this actually does really emphasize a lot of things. Okay, so for part A, it's a closed interval. Okay, so you're literally using the same graph like this. Okay,
Mhm.
but your endpoints exist. That's what the brackets mean. The brackets mean filled in circles there at the end. Is that okay? Is that clear?
Fine, that's clear.
Okay. Now, and actually, maybe I should snip this in each. Oh, I'll do it for the next. So the max is wherever the biggest is. The max is 4, 16, and the min is -2, -20.
Okay.
It's just those endpoints. So that's not all that interesting, but the next one does change quite a bit. So in part B, this probably will raise some questions. Part B, it's the same graph, except these are holes here at the end because of the parentheses.
Mhm.
So there is no max and there is no min. And you might be thinking, well, Matthew, like it's right there. It's right there. Yeah, it is, but it doesn't exist. It's truly the difference between a filled in and an open circle there.
Oh, I think I remember that one. Yeah. Where it's open doesn't work. Same goes for D though. There's none, right? Or no?
Maybe we got to go look at it. So part C is where we've got issues with changing the intervals. So part C, you cannot use the same graph that you've been doing. So what I'm going to do here is go ahead and snip in a new graph here where I only go from, what is it, 0?
0, 4.
Okay. And let me get rid of that. Okay. So let me,
I
I
think the
guess,
min's at 2, and I think the max is at 4 or above, I think.
yeah, on your side, you want to change your window and look at it again. So here, this is a filled in and this is a filled in. So the max is here. The max is definitely there, but the min is now down there.
Mhm.
Max is what, 416. The min is 2 minus 4.
Yep,
Okay.
that's what I got.
But then for part D, where you're now using an open interval,
Mhm.
let me get it in here. Just give me a moment. So it's the same graph, but there are open circles here and here. So when there's open circles, nothing can happen at those points. So there is just a min. There's just a min right here. There is no max. Because there's nothing at the top point here. It doesn't exist. It's like get to the top mountain. I guess it's not there. Not a great example, but
Wait, so how come with oh, all right, so
it's the
the
difference
actual,
between filled in and open circles.
oh, okay.
It's totally the difference. And like, I don't like it, but that is what it is. I mean, that is difference here.
So the next one is just -2 to 2.
Yeah, so you really have to graph it again. And that's what I'm going to do here with just changing the window. -2 to 2. Yeah, so it's so much easier to do in this Desmos. In yours, you have to change your X min, X max each time. These are filled in. Okay, so here, this is truly your min. Your min is truly at -2 comma, whatever we said, -20. Okay, your max though, well, it's right there. And the point of this whole exercise is like the max could be at the endpoints, the min could be at the endpoints, or it could be at the critical points. So your min, your max is actually right there at 0, 0. That's your max.
Awesome.
And then similarly for part F, because it's now an open interval. Okay, for part F, it's now an open interval. These are bubbles. They're not filled in. So it does have a max, as a max at 0, 0, but no min, because there's no there. Now the only example we didn't see that I guess I should warn you about, let me know when you get all this down or if it's clear.
It's all clear. It's fine.
Okay, so the only example we kind of didn't see is, well, what if it's this open here, okay, and it goes up and it goes down, and then it's like this. Well, this has a min and a max.
Oh, all right.
So you have to check. I mean, what you're checking, this is what this problem is trying to, it's checking your endpoints and it's your critical points.
Okay.
All right, so that takes care of that.
And number 7 were constants.
All right, find the constants A and B so that this function has a local max at the point -2 comma 32. I remember we did a few homework problems like this. The mistake is to forget that you actually have to try this point in the original. You have to put 32 is y, a times -2 cubed plus b times -2. You got to remember to do that, because that gives you one of the equations. This is -8a minus 2b. This is equation 1. The second equation comes from the fact that it's a min or a max, and that means your derivatives. You gotta take your derivative, f prime of x, 3a x squared plus b. And this time you don't put the y value in because you want to actually set it equal to 0, but you use the x value, use x equals -2. So you get 3a minus 2 squared plus b equals 0. So that gives you 12a plus b equals 0. And that's your second equation. So you've got equation 1 up here. Sorry, this is handwriting. It's getting a little sloppy here.
How does it turn into 3x squared plus b again with
That's
the
power.
derivative?
That's power rule.
Oh, never mind.
You just bring down the 3, reducing that by 1.
Oh, okay, I didn't see that the first time for whatever reason.
Okay, so you got 2 equations and 2 unknowns. Your best path here is to like say, okay, b is -12a, for example, and then you put that back into the other equation. So it's 32 equals -8a minus 2 times -12a. This becomes 32 equals -8a plus 24a. So that's 16a, a equals 2. You put that back in here and you get b equals -24.
Okay.
And that's your answer. Like that, you're trying to find a and b. Again, you got to remember that there's 2 points. There's the one that's given, that goes into the original. And then you just use the x value. You do not use the y value. Do not use the y value for that because you're setting the derivative equal to 0. The y value of the derivative is 0 in that case.
You say that one more time? I kind of went in and out.
Sure, sure. So like this is the point that you use in the original.
Yeah.
Okay, but you only use the x value in the derivative because you don't care about the y value. You just care about the derivative equaling 0. So that's why you just care about the x.
Makes sense. I think we can go on to 8 now.
All right, sounds good. Grabbing it now. Okay, so this one is they're giving you the derivative. That's nice. They're giving you the derivative and you don't want to take a derivative, like you've got it right there. So it says determine the local min and the local max. That's where you set the derivative equal to 0. So you're going to set 2x squared plus 7x minus 4 equal to 0. This time you got a factor. So this is that ugly factoring that no one likes. It's the guess and check, or you could play around with the 2 and the -4, but I think you can just guess and check here. +4 -1 does it.
Okay.
So you said these each equal to 0.
Looks like 1/2 and just -4.
Yep. Now, there's this thing called the second derivative test. Have you heard of that?
I feel like I have.
Okay, so the second derivative test says if f double prime of c, so you take your second derivative and you evaluate it at like say 1/2. If that is less than 0, you get a max. If you evaluate c and it's greater than 0, you get a min. You're like, wait, you just said less than 0, it's a max, greater than 0, min. I don't make the rules. This is what it is. I mean, it's like just this goes on your note sheet. Okay, so in your problem, you are given g double prime. You're given g double prime of x equals 4x plus 7. So we need to find g double prime of 1/2. 4 times 1/2 plus 7 is 9. Is 9 less than 0 or greater than 0?
Greater.
Greater than 0. So this means it's a min. Min at x equals 1/2.
Okay.
Now we do the same thing for the other critical point. 4x plus 7, g double prime of -4. 4 times -4 plus 7 ends up being -9. -9 is less than 0. So the max at x equals -4.
Understandable.
Okay. Now I'm going to snip in the answer space and you can see what we're going to do next. All right, so here's what we've found so far. We have found that there's a max at x equals -4. That's from this line, and 1/2. The local max of, local min of, you get from putting these values back into the original. But you don't have the original. Huh. That's interesting. So you actually can't do this because you don't have the original function.
Oh, so it's basically missing, it has a big hole in it, basically.
Yeah, you could probably message your instructor and get some points here. Maybe saying, hey, I was trying to do this problem and I want to do this, but I need the original function. I don't have it. You could find the antiderivative of this because you're kind of there in this part of the course, but you need a constant. You need the constant that goes with it. So you can't find it, but you would figure it out by it. Basically it's g. Well, this is the only thing you could do. G of -4, g of 1/2, like whatever it is, that's what your max, but you can't actually get like a number.
Okay. I feel like we're good with that problem now.
All right, now there's a bit more. It says determine the intervals where it's concave up or concave down. So concavity comes from the second derivative. G double prime of x is, what did I say? It was 4x plus 7. Is that right?
Mhm.
Yeah. So we set this equal to 0. And we find that x is equal to -7/4. And then we really need to make that number line there. -7/4. This is for the second derivative. And we test points. We test a number left of it and a number right of it, like maybe -3 and then 0. 0 is always a good one to try, sometimes 1. You're testing them in here, like in the second derivative. So when you put 0 in, you get a positive number. You get 7 actually. -3 in, you get -5, negative number. So this tells you the concavity. It tells you it's concave down from -infinity to -7/4. Oops, that's in the wrong spot. It's the next one. There it is. And then it's concave up from -7/4 to infinity. This is for sure an inflection point. So if it were like plus plus, it would be, concave up everywhere except that point.
Okay.
And if it was minus minus, it's concave down everywhere except that point.
Sounds good to me.
All right, so I mentioned this in that other problem we were looking at. Here's 9. They call it, I guess there's different wording for this, the limiting value. So they're saying, well, what happens? What's the limit in this case as t goes to infinity? And what you're supposed to remember is that for e to the minus t, or e to the minus x, the limit as t goes to infinity, this always goes to 0, because the graph of this looks like this and it goes to 0.
Okay.
So when you look at this thing right here, f of t, as you go to infinity, now this is how you can think about it, or even write it. It's e to the minus infinity, and e to the minus infinity is effectively 0. So this part right here is 0. 860 times 0 is 0. And you probably remember me earlier saying, like, yeah, it's just the top number over this number on the left.
Mhm.
That's the limit.
I remember that in class that she went over this, she said because of diminishing returns that it's that number 125,600 over 2.
Very well could be. I'm going to graph it here and see if I can make some sense of it. There's too much of like a language thing when you say, when an instructor says, it's diminishing returns like half. It really depends on the context. So let me see if I can get a nice window for this. I'm graphing it on my side, trying to 0 to 130,000. There we go. And you said maybe at x equal y equals 1. No, not there. Y equals 125,600 divided by 2. Yeah, so what your instructor meant, and let me snip this in to explain. Sorry, I just gotta get one more thing. There it is. You have the snip. So much faster to graph this on Desmos. All right, so here it is. Your graph here, you can see that you were mentioning this 125,600 divided by 2.
Yeah.
That is true, but it's actually the x value that you care about. It's this one right here. It's where the intersection of that occurs to lead you to the x value.
Oh.
Okay.
All right.
All right. Well, that
Takes us to the end.
probably does take us to the end of the lesson for today. If you do schedule those, we could just pick up wherever we left off here and keep going. But if you have the chance, definitely take a look at these and see if you can work through them on your own.
I'll do my best. Thank you very much, Matthew.
You're welcome.
Do you think that you could do one in-person lesson tomorrow, or is there no time for you?
Go ahead and text me and I'll let you know what I got open for tomorrow.
Awesome.
All
Thank
right,
you very much for
thanks.
your time. Always appreciate it. Have a great day.
You too. Bye.